EE380 yesterday, which was forget to record the whole class. What? Oh, no, I have to do this. I know. Okay. I got to do this now too. Okay. So we're in class and it is exam review day. Homework 3, that's not right. I didn't. Oh, I know why, because I just copied this. It's Tuesday. We're doing the exam 1 review. Homework 4 was due today, and exam 1 is Thursday, February 11th. Unless you made arrangements for me with me to take it online. If you're taking it online, it will be on Wednesday. So there's like 4 people who are taking it online. On Friday, there's an in-lab quiz. Lab 2 will be due, and then we'll start lab 3. Lab 3 will have 2 weeks to work on. It's a little bit longer lab. It involves CMOS design. The pre-lab isn't as much calculations. My recommendation on lab 3 is you're given 3 choices of functions that you can build in standard CMOS. Choose option 1. All of them are equally easy to draw, but when we get further in the lab, the math for option 2 and option 3 is not nice. It's just really easy to do with option 1. So given a choice, okay. On Monday, we're watching a movie in IEEE. It was Ben's idea, and I had actually heard of Asterix, so yeah, I'm going for this. They made Legos out of them. Really popular comic book series in France and in Canada, and apparently parts of Eastern Europe. It's been the movie's been translated into Hungarian and Czechoslovakian and Arabic. Originally done in French, but he's a little comic book character. It's 50 BC. The Romans have invaded, and he has gotten this magic potion that gives him superpowers. He's a tiny little guy. His name's Asterix, and he can defeat the Romans. He becomes really powerful. It's a movie. Watching movies with people, it's something that we've all been missing lately. He's tiny. He's the smallest one in the village. Yeah. No, it's not Lego animation. It's real animation. This is the only, apparently, you know how French people are really big on intellectual property and everything. Every image I could find of this movie I will not let me cut and paste it into this thingy. So comic books I enjoyed reading when I was a kid, and apparently Ben did too. I got them up in Canada. Ben had a German nanny. But we are going to talk about the exam review. Biggest thing I can give you here is I can tell you things that are not going to be on the exam. You can bring in 1 sheet of paper with formulas and diagrams written on it. Take that part seriously, because I found a lot of people learn a lot making that sheet. And then occasionally somebody will come in and say, want to copy someone else's sheet. Yeah, that's great, but you don't know where anything is. The other person may be crazy, may have written everything down wrong, and you haven't learned anything by doing it. So this note sheet, take some time on it. It will really help you out. Save it for exam 2 and the final exam. You'll get an additional sheet for each one of those. You can use a calculator. I'm not gonna police that. Any calculator you want, as long as it's not a laptop. Your ruler might be helpful. A ruler might be helpful. You're gonna have to draw, there's at least one place where you're gonna have to draw some stuff. If your diagrams are neater, it's much easier to give you a good grade, because I can figure out what you're doing. No other electronic devices. If you need to use your cell phone during the exam, even if you're online, I want to know about it. If I hear it, if I hear Discord beeps, I get really upset. Okay. 7 problems total. You can get 104 points on it, 1 point extra credit. There's also a few blanks on the exam, like your quest. If you fill those in, they're an extra credit point. The max score is 105 out of 100. Yes, people have gotten 110 on this before. People have gotten in the single digits on this exam before. No, this is the easiest exam in here this semester. Okay. It was basically a blank exam. They did the extra credit question. They wrote their name on it. And so, you know, it's like, you know, 2 or 3 points right there. If you want to take the exam online, please, I said by Friday, February 5th at 2 p.m. Email me today or tomorrow because the online exam is going to be Wednesday. I can't police both people in the room taking an exam and online at the same time. And a lot of people don't like the online exams. So please email me by, that would be today. This is written on the front page. Any transistor, if you need to know the threshold voltage to solve it, look on the front page. You've got this information. You've got Kn prime, which is mu and Cox. I'm not going to ask you to calculate that. That's actually milliamps, but I can't do lowercase in this particular thingy. You've got the lambda, and that is in per volt, so that's like in the current equation. You've got gamma for the body effect equation. You've got VDDs on the front page. Phi F for the body effect equation is there also. The minimum length on the transistor, if you don't know the length of the transistor, it's 0.13 micrometers. Bunch of things we looked at for in the SPICE deck: charge on an electron, relative permittivity, permittivity constant, and the relative permittivity of both silicon and silicon dioxide. So you can use those numbers anywhere on the exam if you want to. Please answer the extra credit questions. If your answer makes me laugh, or it's a really good one, I give you a bonus point. Stuff we've covered, we looked at the CMOS inverter and those noise margins. Think lab quiz 1. Yeah, you might see something like that. The MOSFET structure, we looked at cross sections, what the different materials and doping were, and what it took to form a channel. Knowing the symbols, I'll tell you what question 1 on the exam is, because I don't want you to miss it. You've got 4 different transistors with voltages on them. First question about each of the transistors, is it PMOS or NMOS? Second question is, what region of operation is it in? So be able to do that. Question 2, we'll get into that. Okay. So inverter delay and power and some more complex CMOS circuits. We looked at standard CMOS, and then later on in section 2, we looked at past transistor logic circuits and dynamic logic circuits. There's 2 logic circuit questions on the exam. It will either be given a function, draw the schematic for this using either one of those 3, past, standard, or dynamic, or something where I give you the schematic and I say, what's the function? So you be able to do those. Those are the problems that most people do good on. It's not like the on exam 2 where you have to use KCL and KVL and Ohm's law. I'm sorry. Other things that we looked at in here was the body effect. It's always important. I don't have to tell you on a problem to look at the body effect. If you know what the body voltage is, you've got to take and the body to source and the body VBS is not 0. You've got to take the body effect into account. We'll lose a few points for that. I've never put a capacitance problem on this exam because it annoys me, and I've never put a latches and flip-flop problem on there. So the three things you want to concentrate on for this section is body effect, those pass transistor circuits, and those dynamic logic circuits. And one thing I found is if you get a screening interview with Micron, they are overwhelmed with how good NAU students do on their screening interview, because their screening interviews usually happen right after exam one, and it's the same thing. So yeah. Okay, somebody's chatting at me. Thursday exam is in the 188 lab, EGR 234. Same place where you had the EE188 lab. I don't think anybody took 188 during COVID. Thank goodness. Really? The one, oh, but that was the first semester. Okay. It's not as bad as it is now. No. I have taught 188. The last time I taught it was 4 years ago, and that was because Dave Scott died. I did it as a favor to Dave. He was really sick at the start of the semester, and the choice was, well, Julie, either you teach it or Dave teaches it. And I said, no, I'm going to take care of Dave. He's not doing well. Yeah. The lab now uses these little boards that you're supposed to measure things on that don't work. Not the oscilloscope, because we can't send the oscilloscopes around the world. I miss Sam too. I had nothing to do with that. So from lab 1 and lab 2, we haven't done the lab 2 quiz yet, but that lab 1 quiz, you might see something like that on the exam. The instructor questions. Sounds horrible. Yes, 188. I don't want to touch it. It was bad enough teaching 110 remotely last semester. I had 5 lab sections. And they're freshmen, and we did it all on those FPGA boards, but I already had it written for that. So the MOS symbols, the basic ones look like this, and the way you can tell, I won't tell you that. These right here are NMOS. Oh, I do have my little screening thingy. These are NMOS. The arrow goes out. The arrow indicates the direction of current flow. The arrow's on the source. And the source is always the lowest voltage. VDS is always positive. Let me put it that way. For A is greater than 0 for an NMOS. So that's a source. This is the gate. This is the drain. This is the drain. And the 4th terminal up here is the body. And you'll be building circuits with using the 4-terminal version in whatchamacallit in lab 3. These right here are PMOS. Again, the arrow indicates direction of current flow. For PMOS, VDS is always negative. So we draw the higher voltages up at the top, the source goes up. Drain, body, gate. Gate, source, drain. Okay. So that's a good thing to know how to do. There will be a 4-terminal, on the first problem, they're the 3-terminal symbols. They look like this. They literally look like those symbols there. On problem 2, because this is what multi-sim will draw, there is a 4-terminal transistor using this funny little thingy right here. The arrow is not on the source, it's on the body. And when it's on the body, the outgoing one becomes PMOS. Yeah, because it's drawn upside down. And the one with the N going on the body is NMOS. So be able to tell the difference between those two symbols. Also, PMOS, we usually put the higher voltage on the source, so it's going up, the drain's going down, the gate's over here. And NMOS, the drain's up at the top. So those symbols, those are important to know. All of these symbols are important to know. Okay. This is like the lab 1 quiz. And what we did in the lab 1 quiz is looking at this voltage transfer curve, you want to estimate VO high, VO low, and all that stuff. So what you do is you come in here and you sketch a place where the slope looks like it equals -1. And there should be 2 places here. I got 2 places there. And then I find the X and Y coordinates for these. So there's the X. This is the output axis. So this is going to be V out, and it's a high voltage, so it's VO high. The X coordinate goes down here. It's on the input axis. So this is VN, and it's low. It's the lower voltage. And then I can come in here, and I've got VO low, and I've got VN high. Just finding, and you did that in the lab. There was a VM in here too. VM is where V out equals VN. That's a W. VM is where V out equals VN. And the noise margins are basically the difference between these 2 voltages. That would be the noise margin low. The noise margin high would be the difference between these voltages. I can never get my subscripts right, so I just subtract them and then make the answer positive. It's a positive number. So that's what we did on the lab 1 quiz. This is the top view of a MOSFET.
Oh, excuse me, I had a question actually about
Yeah.
the last one. Sorry.
Okay, go ahead. Good, Sean.
So, can you also classify the output voltages OH and OL as just any point past or any point behind, any point before the transistor region? So, like VOH can technically be just the highest point on the graph, VOL can technically be just the lowest point.
Okay.
That's what I've been doing on.
Okay, you're supposed to actually look for the place where the slope of those lines is -1. Right here, this would be what we call, in the engineering world, we call worst case. The circuit is still functioning, but it's giving you the worst possible output values it can and still be called functioning. If it goes into this region, it's linear and it stops working like a digital circuit. Now, a lot of times on the data sheet, they post 2 values for VO low and VO high and all that stuff. They put the worst case in here, and they put, well, this is like the average value I get on these coming out of the line, and they call that typical. And for your design, you've got a design so worst case still allows you to pass your spec. But if you're worried about power consumption and things like that, the typical values are usually pretty good too. So you kind of do 2 models of your design, one at worst case, one at typical, and see how it changes between there. Okay. We have the top view of a transistor. This is actually an inverter. It has both an NMOS transistor and a PMOS. We know the top one is PMOS because it's got the P plus diffusions. So this is my PMOS, and it's bigger too. That's a hint that it's PMOS. And the bottom one is NMOS because it's smaller and it has N plus diffusions. So the drain and the source are completely symmetrical. What determines what's the drain and what's the source is, in an NMOS, the drain's tied to the highest voltage. And you can swap them. And there's actually, I've seen circuits in 490, and I've seen circuits in the real world where In some modes of operation, the drain's on the left, and in some modes, the drain's on the right. And it just kind of swaps between, because they're perfectly symmetrical devices. So this NMOS, I'm going to call one the drain and one the source. I'm going to call one the drain, one the source right here. The gate is actually the place where this active region, what's inside the yellow line, intersects my poly line, and my poly is part of what forms the gate. So the gate is that little region right there. The width is the distance going from the drain to the current going from the drain to the source. How wide is that? So the width is in this direction, and it only goes to the yellow lines. And the gate the length only goes through the lines right there. Same thing on the bottom. It has a much smaller W because electrons move faster than holes because they weigh less. That's real. Oh, good. Somebody caught that. I've gone whole semesters where I've said holes weigh more than electrons, and no one has batted an eye. Yes. The active region is kind of like this green square. It's where I've got the N plus and the P plus diffusions. The diffusion goes, it goes, it's doped and it's allowed and it doesn't have field oxide. So what is really active region when you start looking at these cutouts on like lab 3 and lab 4, it's absence of field oxide. But we define it as a region because when we're making these things, we have to have these region boundaries where we don't want to put field oxide. We put field oxide on everything that's not active. So I'll actually put insulating layers every place where I don't have active underneath there. And so we give it a name, but it's not really anything that I have to do other than not put field oxide there.
Okay, so it doesn't actually affect your operation. It's just...
Yeah, but it limits the region that the transistor can operate in. So the transistor can't operate if there's field oxide. So this what's the yellow line is becomes the transistor. Okay. So we got W over L, and we can do some basic measurements. I've looked at these diagrams before. Had to make them.
Isn't that bad? Like, wouldn't you want your toothbrush bristles to be somewhat hard so you could actually brush away the plaque instead of brushing?
Okay. All right. We want to look at the shape of the channel. These cross sections, yes, pictures that look like this have shown up on my exams before. This has N plus diffusions. So it is an NMOS up at the top. Hold on. Yeah, I know. I don't auto-mute people. It's okay. I don't mind. That's better than a lot of the things I've heard. In 110, it would usually be freshmen screaming obscenities at each other. Okay. So this is an NMOS. I don't like muting people. This is a PMOS. We know it's NMOS because of the N plus diffusions on the source and the drain. So would you be able to label this diagram? Micron might ask you to do that in a screening interview. The body for NMOS is usually grounded. It's a P plus diffusion to give you a good low resistance contact into the body. And then the gate's right here. PMOS, all the letters get switched. I need N plus diffusions. I need P. That's not right. They're the same one. Yeah, say that you're right.
You just want another channel.
P plus, P plus. I'm gonna make it P plus. I want to talk about, and never mind. Okay, so we've got this here as an NMOS. The way I get current to flow, normally I have back-to-back NP diodes in here that cannot conduct current. If I put a voltage at the gate that's positive and it's above V threshold, I'm going to start to form a channel right here. And if I'm in triode, the channel goes all the way across. And the channel is going to be caused by the positive, this is a voltage, this is a capacitor. I'm putting positive charge on the gate, and which attracts negative charge out of the bulk into this region right here. Now I have an N region, so current can flow. This is in triode, and as VD, let me just draw a better picture of it here. So this is in triode. Now if I go into saturation, if I increase VD, what happens is I stop forming a depletion region at this end. So in oh, I'm using the pencil. Okay. In saturation, as I increase VD and go into saturation, it starts pinching off the channel at that end. Okay. About everything you need to know for the micron screening interview.
So the triode, it's going to have like a flat channel?
Yes.
And saturation is going to have like a slightly.
It's going to be pinched off at the end. And that's the reason why, as I increase VD, the channel keeps getting smaller, which the resistance goes down, but then the current, it's like it balances each other out, and you ideally have a constant current source through there because the resistance is going down as the voltage is going up. Or the resistance is going up as the voltage is going up. So the current stays the same. I said it right the last time.
And a question.
Yeah.
Does this actually affect like the depletion region of the transistor, or?
The depletion region. There'll be a depletion region. Let's go to this diagram. There'll be right here I have a PN junction.
Yeah.
Let me erase all of it. This is still almost. I wasn't looking at it. But I've got these PN junction diodes. And since they're PN junction diodes, they form a depletion region on both sides of these. As I increase the voltage difference between the body, which is this P side, and the source, which is this N side, I'm going to, if I have a bigger voltage difference across there, still reverse bias, I'm going to increase the depletion region size. That's what's going to cause the body effect. Yeah. Questions? Okay. This, you're given on the front page. You're given this number right here. You don't need to calculate it. This number right here, this is called the transconductance parameter for the process. It's good for every transistor on your die, and it should be the same across the die. It changes from day to day, but if I want to find the transconductance parameter for a particular transistor, I just take Kn prime and multiply it by W over L. We'll go prime crazy like after this exam. There'll be RDs and RD primes and RL primes and RLs, and they're different. Just remember the prime means something. I didn't believe that at first. Okay, we've talked about this. As we increase VD, the channel gets narrower at the drain end. And that's what causes it to go in saturation. The resistance goes up, but the voltage goes up also. And so the total current through this device is the same. These are the ID curves for a transistor. ID versus this axis is VDS. This particular curve is at a particular VGS. I've got cutoff down here, no current. Triode, the current is increasing as the voltage increases, and then it flattens out as it starts to go into pinch off. Problem 1 on the exam. Identify the symbol. Is it PMOS or is it NMOS? Can you tell me what region of operation it's in? If you know those voltages, you know which is the gate, which is the drain, and which is the source. On your transistor, you can calculate VGS. VGS, remember, is just, it's a voltage nomenclature thing. It's VG minus VS. Yeah. Get some practice with those. If you wanted to calculate current, these current equations are good for both PMOS and NMOS. And they're approximations, I'll tell you that. These should actually be big ID, and you'll understand why that matters in a minute. Big ID is the current without the channel length modulation. Remember, we include the effect of R out, we have to multiply this by 1 plus lambda VDS. You only do that in saturation. Never multiply a triode current times 1 plus lambda VDS. Guaranteed to get you a point or two off. Once you know, you can get this off the front page. You know the size of the transistor. You can figure out what VGS is. You can get this off the front page. You may have to recalculate it because of the body effect. Remember, that is body effect dependent. Unless I tell you to ignore the body effect, or VBS is 0. Okay, there's some practice, and these are all solved in the slide solutions. Lambda's 1 over VA. I don't need to know that for this exam because lambda's on the front page. We'll get to that later on. We got to that in the homework. This part right here is usually referred to, the normal nomenclature is big ID. And little ID includes the effect of the channel length modulation, the 1 plus lambda VDS. Okay. The output resistance, you don't have to worry about VA because our lambda's on the front page. It is, this is a gimme, don't miss this problem. Oh, this will be on exam too, mostly. Little RO is 1 over lambda ID, big ID, and big ID is the part that does not include this. This is big ID, this is big ID. So I made that mistake on the homework and somebody caught me. It's little ID.
In this case, we're not gonna have to worry about little ID then.
I might ask you on a problem to calculate little ID. I might ask you to calculate big ID. This is the one case where I will get the case right.
Couldn't you get other than obviously to change the equation, so I mean, like, conceptually speaking?
The big ID is the current that you would have if that channel wasn't pinching off. And there's a couple of ways we can model that. And you can model it by actually going through and including the 1 plus lambda VDS and calculating the real value. The other way is you can take the small signal model and I can throw in an imaginary resistor that only exists in the AC model and call it little RO. and put that in my circuit analysis program. And that's the way PSpice does, is it models each transistor as an array of capacitors, resistors, and dependent sources. There's no inductors because inductors don't really exist. I'm a microelectronics person, I can say that. And now I'm working with MRAM and it's inductive. And so, okay, never mind. Power people love inductors. I don't. They're big, bulky, and expensive. Okay. We'll talk more about the effects of RO and how we model that after this exam. Dynamic power, you don't need to worry about this too much. Just know that the big thing to get from this is the dynamic power increases as the frequency goes up. It increases if the load capacitance goes up, and it increases as VDD squared goes up. And so if I can lower VDD on my chips and have like 1.2 volt parts, 0.8 volt parts, I can, and still have the threshold voltages in the right place, I can build more transistors on a chip without having too much dynamic power dissipation. And this power dissipation leads to heat, which leads to your devices melting off the board. Like what was the Xbox was really bad with that. I don't know if you guys remember the Xbox or not. The first version of Xbox they had the main processor was on this beautiful heat sink to get the heat off the chip. But nobody thought to put a heat sink underneath the graphics processor. And this is a gaming console. This is where the graphics are what gets used. And so what would happen is the solder joints would actually melt underneath there and they'd stop working. And at my old school, I was teaching it before here, one of the guys had this cottage industry fixing Xbox. It's just basically reflowing the solder on there and making them work again. And he brought one into class one day, and this girl had played her Xbox for like 24 hours straight and somehow managed to melt the graphics processor off. I mean, it was off the pads and off the board. It was like sitting on the side. There was no way we could resolder that. So we just demolished the whole thing with a heat gun. Things you're doing have spiritual. We had a 2-hour break between classes, so we didn't have much else to do. Short circuit current, you'll see more of this if you take Dr. Yeramasu's power classes. It's basically if Vn here equals VDD over 2, both transistors are on, which means I have a short circuit between ground. This is my Vn is VDD over 2. I get my peak current there. A lot of good jobs in Arizona for power engineers. A lot of companies use it as, yes, Zach, recalculate VTN if there is a voltage between VB and VS that's not zero. Okay. A lot of good jobs for power engineers in the state too. Companies like General Dynamics and Raytheon use it as kind of like an entry-level job. If you know how to build a 5-volt supply or a 2-volt supply for a board, they'll put you on that starting out. There's also some jobs opening up too for PCB designers. A lot of times you don't get that in school. It's easy and fun to do. You just have to know the rules. Take my 490 in the fall. It's not that hard and it's fun. Yeah.
Regarding the body effect, are we going to be told where the body of each transistor are tied to, like similar?
If it's a 4-terminal transistor and you know the voltage and there's a voltage at the body, you'll know what its voltage is. If I give you a value of VB in the problem statement, you know what the body voltage is. If I give you a value of VBS in the problem statement, that's a big, and it's not 0, that's a big tip off. You need to look at the body effect. Problem 2. Okay. 49. Oh my gosh. Okay. These standard CMOS circuits we've been doing since 280. With the NMOS side, if I want to make an OR function, I put them in parallel. If I want to make an AND function, I put them in series. I flip that for the PMOS side. So if I give you the PMOS half of the schematic or the NMOS half of the schematic, I would take all these series connections and make them parallel, and I take all the parallel connections and make them series. And make sure you hook up your VDD and ground. I care. It doesn't work without VDD and ground. The thing about this is you've got to remember this is an inverting structure. So once you figure out your ands and your ors, you put a bar over the whole expression. Don't forget that. There's going to be two problems on logic. One of them will be standard CMOS. So here I need both the pull down network, which is the NMOS part. I need the PMOS part, which is a pull up. A and B are in parallel here. So they go in series up here. C is in series with a parallel combination of A and B. So now C needs to be in parallel with the series combination of A and B. The logic function looking at this is I have A or B, and that whole thing is in series, so it gets ANDed with C and put a bar over the end. This is probably the easiest thing you're getting on this exam. On this, yeah, we tweak it. Analog's just a lot more math. It's not really that hard. You got to remember some of the 188 stuff. Okay. W over L equivalents, you may see these on here. How we find the W over L equivalents, we take the W over L of each one of these. 5, W over L is 5. You can reduce fractions, it's okay. If I said it was 10 over 2, that's just 5. I could have written it a different way. We want to find the W over L. They add like capacitors. So A and B are in parallel. So A parallel B. I add them together, becomes 5 plus 5, which is 10. And that is in series with C. So C series, this is the way I did it when I used to teach 188. A parallel B becomes 5. It's product over sum. Remember, for a parallel combination, over 5 plus 10. So 50 over 15. It's a number. 50 over 15. It's 10 thirds. 3 1/3. We got that. Okay, carry on. I'm not going to do the thing where things are switching in low and high and make you do that. We'll do that in the lab where I'll be sitting there and helping you with your confusion. That's lab 3. The body effect equation is right here. I told you it's always important. Gamma is on the front page of the exam. You don't have to calculate it. Worst thing you have to calculate is this. You're given phi f on the front page. You're given gamma. You're given VT0. You can get VSB, the magnitude, so it's always positive, on from your circuit diagram, and you can calculate that to get your new VT. Okay. I give partial credit. Basically, if you make a small mistake on the front end, and I can pick it up, and I try to look at your work and see if you could possibly have solved the problem that way. I stopped debugging students' algebra years ago because it was driving me crazy. So the next question is, could you have possibly solved it that way? And if you could possibly solve it that way, and I can identify your problem, I'm only going to take a couple of points off. I'm not going to go through all your calculations over and over again. I grade them myself. Sean may grade more thoroughly than I do. Capacitance. Don't spend. You can look at these things if you're really interested in them, but I just find that they're too long of problems for the exam, and they're not really practical. For an entry-level engineer, this isn't the stuff you need to know. I'm just having fun doing this. Okay, things I do care about. These different alternatives for doing CMOS logic gates. Static CMOS is the workhorse. It's what you're going to see in your processors. It's what you're going to build in your designing an FPGA circuit. It's the most reliable, the most robust. Sometimes, very often, you're designing custom IC. People who do that in Arizona, my first word is going to be Micron. Okay, honorary Arizonans, Micron, because I hire a lot of NAU students. Intel, onsemi, NXP, Maxim, Viasat, General Dynamics, all those companies down in the valley do this at some level, and some of them end up selling them. So these are where the jobs are. You get this custom IC, you're going to have a situation where the logic just doesn't fit, and that's always the problem. It just doesn't fit. It's too big. Too big. So I go to one of these other alternatives to save some space. I've never put a transmission gate problem on here, and this is a transmission gate. The version that you would get of this circuit would look like this. I just use straight pass transistor. B and C. Sometimes I ask people to draw the circuit given a function and think about that Shannon criteria. There's got to be a low impedance path to ground. Sometimes I tell people to, given the circuit, what's the function? That's the easier alternative. Dynamic logic, I add these two transistors and I get rid of the pull-up network, and that generally saves some space too. This has threshold loss problems. Remember, you lose a threshold. So I'm doing horrible things to my noise margin. This one has timing issues. And depending upon where you are in the circuit, you're okay. Generally, as a pop engineer, it's more like, this thing is broken. Just go out and tell me what's wrong with it. And then you come back a week later and you might have something intelligent to say, or not. It's a lot easier job than the school makes it sound like. And generally what I would do is, if I couldn't figure it out, I go out and talk to people. And engineers are bored and they love it when people ask them questions about technology. And make friends with the technicians. Technicians know the nuts and bolts of everything. And if they don't like you, they can make your life miserable. And if they do like you, they can make you look like a rock star half the time. Yeah. Get them coffee, talk to them, smile. Yeah. In some ways it helps. In some ways it helped being a girl. Guys are taken more seriously, but as a girl, I could walk into anybody's office. There were people at E-Systems that would hide from people who were looking from them. But if they saw me coming, I could get, people would just give me stacks of stuff that they needed to get signed sometimes. This was my intern job. Because I could track people down. Sorry. So you get advantages and disadvantages both ways. So for this pass transistor AC, it just implements the AND function on the gate, and you will get the pass transistor version, not the transmission gate. If I want to OR something together, I just tie the two outputs together. Y equals X or Y. X, something like that. This output equals X or Y. Okay, here's one. Just look, I ask you what the output is. You get this as an exam problem. I go through and I label each of these nodes. This is BC. This is not B and 1, which is just not B. I'm going to do the Boolean reduction there. B or not B or BC. This one shows up a lot, this Boolean theorem. This is just going to be not B or C. That's one when I was first teaching 110, I just write down, and I had a little cheat sheet next to me. That's a theorem. So this is not B or C. ANDed with A. A lot of people don't have problems with this logic stuff. This is A naught, C naught. And then the output would be, I multiply it all out, A naught B or AC or A naught C. I could reduce this because it doesn't matter whether A's high. No matter what, if C's high, that expression will be high. So this is AB or C. I don't take a huge number of points off if you don't do your beliefs. Okay, I realize people don't like that. But if you could at least write the long-handed function right, I'm usually fairly happy. There's some design examples, and I probably, yeah, there's something. Oh, I need to get to the other thing. This is in the slide solutions. I create a pass transistor circuit to do this. You get a practice with a few really simple ones. I'm not going to give you a very complex function because you only have 10 minutes to think it out for a problem. It's an exam. I'm going to keep the problem short and relatively simple. Yeah, I didn't do that. I didn't do that. I've never done that. Dynamic, I have put in dynamic circuits on there. Ways I could do this, I could give you a function and ask you to draw the dynamic circuit. You always put the PMOS and the NMOS clock transistors on there, and then you draw the pull down network just like it's standard CMOS. This is inverting just like standard CMOS. Pass transistor is non-inverting, so this function here would be A in parallel with a series combination BC and put a bar over it. You could draw the function, you know, if phi is low, the output's high, no matter what. Oh, great. Oh, it's been a while. It has.
Oh, man.
I got through like the last on Thursday. I didn't. I'll be back in a minute. If phi is low, the output's high no matter what. If phi is high, the output depends upon the function A or B, C naught. I'll be back shortly.